Well, the first paragraph, and as I told you, this paragraph is all about the phase of the changing Earth. And, well, you might have seen pictures of our planet, the way it, well, we think, looked millions of years ago, in the time that there were dinosaurs, in the time that there were only bacteria. And when you're looking at those eras and you're going to look at the way our planet looks today, you may notice that it is very different. And to understand that, it is very important to have a look at the history of our planet. And what we're going to do is that we are going to look at how the Earth was born. This is the thing that I just told you. You don't need to learn that because it's just a little bit of side information. And these two are actually in your book as well, so you can find uh, the information there as well. But first, how was our Earth actually? To understand that, we have to go way ahead. As you might know, in our solar system we do have a sun. And the sun is the center of our solar system, and the planets are actually twisting around that sun. But when you're looking at older solar systems, at some point the sun or its star in the core of the solar system is going to die. And when it dies, it explodes. And when an old sun or old star explodes, it's called a supernova. And when that happens, it creates an enormous force of energy, and that energy is actually pushed into the universe, so to say. And it creates what they call a shock wave. It's like a very high pressure of air, but it's not air, but it's pressure. And the pressure is very important. In the core of that star, there are lots of elements. And I was wondering, do you know what elements are? And then we're talking about the elements that we use in nature science. Does anyone know what kind of elements there are? No? Think of helium, think of gold, lead, but all kind of gases. And those elements are actually saved inside that star. But with a supernova, all these elements are being pushed out and are flying somewhere around us in the universe. But when you're looking at those elements, they differ in weight. There are heavy ones and there are light ones. What does happen if I drop a block of lead here in front of me? What does happen? What does happen with a block of lead when I drop it here? It falls on the ground. But what if I do the same with a feather? What happens with a feather? Yeah, but which one is faster? The block of lead. So what happens is those heavier elements will, well, actually do not go that far from the core of that original star which exploded. And the lighter elements will go further away. And that is something which is very important. Why is this important? Our planets contain elements, and those elements are different. And why are those elements different? Because our planet, these planets are on different angles from our sun. So what happens is that the heaviest elements create a new star, that's our sun, and then you got all the planets, like Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. And all these planets exist out of different elements. You might know that the first four planets, Mercury, Venus, Earth, and Mars, contain out of rock. And the other ones contain gases. And gases are lighter than rock. So that is a thing to think of. Why do we have a planet which contains rock? Because we are closer to the sun and closer to the original supernova. This is difficult to understand because it's very abstract, but I try to well, show you a way of why planets are different and why we do have water and why Mars doesn't have water. Yes?
Notebook, or can we just see the PowerPoint.
You may see the PowerPoint here, because this is just something I want to add to the book, because it gives you a little bit more inside information to understand what's happening next. So what happens? The heaviest elements became part of the new sun, our sun, and they're still active. When we are outside and we're during the summer walking around somewhere, we feel the heat of the sun, and that's because of those elements are actually bonding together. There's what they call core fusion. The cores of atoms, they are being fused together, and it gives a lot of energy. So that energy is what we are actually feeling here. The less heavy particles, the less heavy elements, they are floating further away, so they bind later on, and that creates our planets. And when we're looking at that, I will show you. We do have a solar system. So actually our solar system exists solely out of elements that came out of that supernova once. And we were lucky, because our planet contains the elements that make life possible. So the reason that there's life on our planet was actually created by the fact that we had the right amount of elements that were pushed into the sky, into the universe during that supernova. So that was very important for us. But there happened something else. During the beginning of our solar system, the planets, they weren't solid yet. So there wasn't a rock crust around our planet. So it was a molten ball of lava floating around the sun. And at some point in time, another planet, it was Mars-sized. If you look at it, Mars is a little bit smaller than the Earth. It collided with the Earth. And when that happened, a big portion of the Earth was pushed into space. And that became our moon. And how do we know that? Of course, people were on the moon, and there were several trips around the moon. And they drilled holes inside the moon to collect information about the elements. And what did they find? The elements on the moon are exactly the same as on our Earth. So it was pretty weird for them to understand that the moon was once a part of our planet. But then we're talking about 4.5 billion years ago, so that's a long time ago. So why does our moon contain the elements of the Earth? Because it was a part of the Earth. So then you might think, why isn't there life on the moon? Well, there's a little problem. The moon is not active. That means it doesn't have a core, it doesn't have magma, it doesn't have volcanoes, and even more important, it doesn't have an atmosphere. And the atmosphere is important for life because it contains gases which protect us from radiation from the sun. And on the other hand, it could create water like rain. It could create shade for us. And it, as I just said, it protects us. So that's a problem here. So this is the first part, what was happening during the first, million years of the creation of our planet. Later on, life emerges, and that's the thing that we're going to start with now. So now we're actually going to start with the things which are in your book. And was this. Our planet became solid, which means the crust on the outer skin of our planet started to, became solid, so that later on animals and we, of course, could walk on it. And when that happened, gases escaped from the rock into the sky, and that created our atmosphere. As I just told you, we do need an atmosphere, because without an atmosphere there won't be any possibility for us to live. And very important, of course, it created water, and water was the main ingredient of our planet for getting life. So 3.8 billion years ago, our planet got covered with oceans, and as you look at this picture, they think that our planet looked like this 3.8 billion years ago. So you see, it looks very different from now. And it was all to do with the fact that the continents, they were there, as you see on the map, but they weren't at the same spot. because continents drift. They are moving around our planet. And that, of course, alters the way we look at our planet. It looks different because of the fact that, for example, many years later, all those continents were stuck together on the middle of our planet. Do you know what the name was of that supercontinent? You might hear that later. Yeah? Okay. Yes, Pangaea was the name of the supercontinent, but that is, I think it was 500 million years ago. So that's not as far long ago, I mean, than the 3.8 billion years ago where we're talking about now. But still, there was no life on Earth. Life started to grow somewhere about 3 billion years ago. So 3 billion is 3 milliard years ago. So that's, well, a long time ago, but it took many millions of years before life, well, could exist here. And what kind of life did emerge? Well, we're going to look at it. One-celled, well, life. You can call this life. Unicellular creatures, and if you would have wanted to give an idea of how does that look, if you would use a microscope and look at a bacteria, that could be unicellular. This, if you're talking about something like a bacteria, that was the life there was. And that was during a very long period of time. What happened was that those unicellular creatures had to develop itself. And we think that it took about, well, it started to grow, as I just said, about 3 billion years ago. And 500 million years ago, it developed itself to creatures which could swim around in the sea. So there wasn't life on land yet. So those bacteria became small fish or shrimps or other kind of animals, and I will show you them on the next slide. Of course, unicellular creatures are still there because bacteria are still there. So those are actually the oldest living creatures on the earth nowadays because they already existed several billion years ago. So they're pretty old. These kind of animals emerged around the end of the first era that we are going to look at later on. And you see that those animals do like, they do look like a little bit like animals that there are today. I mean, they are different, of course, but there are some similarities. If you're looking at this one, this Anomalocaris, it just looks like a shrimp. It is not, but it does look like it. Trilobite does like a snail. Yeah, a snail. Yes, it looked like it. But there's some difference between this one and a snail. This one, it does have a shield. So that's different. And they lived during a very long period. And they could be very small, but very big as well. And then we do have another one, the Haikuichis, and that's a fish kind of animal. But as you might notice, it just looks a bit different than fish than we see nowadays. But during this period, and that is the Cambrian, that is the second era, these developments went on very fast. So those animals developed very fast. So they changed, they altered their the way they look. And all kinds of animals emerged out of those unicellular species. Shellfish, sea urchins that are zeeegels, arthropods. Sea urchins still exist. So next to the bacteria, these are quite old, to say so. I mean, dinosaurs do not exist anymore, but these creatures are still there. If you go to the sea, the Red Sea, for example, near Egypt, you can find sea urchins. So they already existed 541 million years ago today. If you see this, MA, it's means mega annum. That is actually the same as they say if you're somewhere in computer language, megabyte. It means the same. So you're talking about millions of years ago. So that means you're looking at 541 million years ago. Yeah. Um, this is very important. This is in your book as well, so you don't have to write it down in your notebook. These are all the eras that we do use. So we're talking about the geological time scale. And we started with the Precambrian, and that's the area of the bacteria. So this is the period that we only have the unicellular creatures. Later on, you see the development of all the animals and types of animals that do walk around or swim around on our planet. And what I'm going to do is to show you the eras and some parts of the periods, so that you have an image of what lived during a certain era. And we're going to, as I just said, with the Precambrian, and this is a very important part of our history because here life starts. So during this period, which was very long, as I just told you, 4.6 billion years ago until 550 million years ago, so that's an enormous time span, we only had bacteria, nothing else. Well, we think that there were only bacteria because we do not know a lot of this era because there is not much continent left which was already there during this period of time. There are small parts of the Precambrian crust left in the United States. If you go to the Grand Canyon, you may find some Precambrian rock, but that's all. So during this time, the Earth was different from what it looks like now. As the text says, the Earth froze sometimes. That means that it was like a great ball of ice. And that was the reason, of course, that life could only exist beneath the surface of the sea, because the sea wasn't frozen. The continents appeared. That was the solidifying of the crust, what I was talking about earlier. And at the end of this period, we're going to the Cambrian era, the Paleozoic. Life started to change, and that means that from the bacteria on, we get those arthropods and sea urchins and all that kind of animals which were swimming around, and of course walking around on the crust. So we're going on to the next one, and I'll pause it for a while. The second era, the Paleozoic, and as I told you, those eras contain the periods. So these periods are part of the Paleozoic, and you see there are how many are it? 7 of it? 6? 6 ones. And during the Paleozoic, the animals got bigger. In the beginning, we only had those small bacteria, and because of the moving continents, the continents start to move together at the end of this era. We got Pangea, what we were talking about earlier. Animals could walk across our planet, and that was very important because at the point that animals were capable of visiting each other, seeing each other, they could eat each other, because when there's enough food, animals tend to get bigger, and they could create variations of their own sort. I mean, they're going to create little animals, of course, and when that happens, well, certain species are actually, well, bond together, changing their appearance, and all kind of animals developed during that era. At the end, as I told you, the supercontinent emerged, and at that point, life is very diverse. That means that we got fish, we got land animals, we got the bacteria, of course, as well, and that means that there is a lot of life on our planet. And earlier, there wasn't. So it changes the appearance of our planet. But still, the animals on land are not that big. I mean, the dinosaurs weren't yet born, so to say. So they had to develop. And as you might know, dinosaurs are very big. I don't know if any one of you did ever see a skeleton of a dinosaur. Did you visit the Naturalis Museum in Leiden once? Yeah? Well, there was, I don't know if it's still there was a skeleton of a dinosaur. And when you're standing next to it, you might have noticed that it's pretty big. I mean, you don't want to encounter a dinosaur when you're walking on the street. I mean, I think they think that you're a nice lunch. Um, during the, the first period in the next era, the Triassic, the dinosaurs got. And that means that plants and animals start to change. There is more food for the animals, and there's more food because of the fact that the animals get bigger. I mean, a Tyrannosaurus Rex got that big because of the fact there was enough food. Like human beings, when we eat too much, we get bigger as well. Not that healthy, but it does happen. And the same happens, of course, with animals, but during this period, which is, of course, pretty long, 50 million years, they got bigger because of the fact that there is enough food. And as you might know, people get bigger, and then not that way, but that way as well, because of the fact that the quality of life gets better during the years. I mean, when you look at a house which was built in the 16th, 17th, 18th century, doors were pretty low. I mean, a door of 1.90 meters was enough for people to walk through. Nowadays, the rules say a door needs to be at least 2.30 meters high because people tend to get longer. Well, the same thing happened during the first periods of the era Mesozoic, during the Triassic and the Jurassic, because, well, they get bigger and bigger. And something else happens. Pangaea, the supercontinent, divides again. That means that animals are not all on one continent anymore. And that means that during those change of the way the world looks, the animals had to live with everything that was on the continent they lived on. So at that point of time, the way the continents look changes as well, because you might know that when a continent is, for example, near Antarctica, the temperature drops. So those animals, for example, needed feathers, because without feathers they won't survive. But when they were near the equator, in the center of the Earth, the temperature might rise, so the temperature is hotter, so they might need more water to live. So animals change because of the changing appearance of the Earth. And then we are at the last one, and that's the Kenozoic. And that's the era we are living in today. And during the Tertiary, the dinosaurs got extinct, and life as we know it now starts to emerge. It means that, for example, the first mammals came around, like us. They didn't exist before. And during the Quaternary, human beings started to arrive. So, if you're looking at these whole time span, we're only a very small part of the history of our planet. And by now, we are changing our planet, of course, because we are with a lot of people. And in the past, of course, there were many types of animals, and probably some groups of animals were just like us, with too much of them. And what happens with a planet if there are too many of one species? Does anyone know what happens when there are too many of one species? Yeah?
Maybe it takes over, like killing other species.
Yeah, exactly. What we are doing now is that we're using all the things that are available on our planet. And of course, at a certain point in time, there is nothing left. So what can we do when there is no food left? And next we're going to talk about the mass extinction. And mass extinction, of course, leads to the decline of a certain group of animals during a certain period of time. And maybe at some point in time we are with so many people on our planet that the amount of human beings is going to drop as well. So maybe we get extinct once as well. Not in a few years, it will take 1,000,000 years or something like that, but it might happen. And then there will be a next era without us. But what are reasons for mass extinction? There are several reasons for mass extinction, of course. And when we are looking in the past, we might notice that climate change is one of the biggest events changing the life on our planet. Because what would happen if the temperature on Earth at this point of time should rise with, well, let's say 10 degrees? What should happen to us when the temperature rises with 10 degrees now, today? Does anyone know what happens? No? Well, there will be certain, yeah?
Maybe land becomes dry with less water
Yes, land becomes dry and we can't live there anymore. It becomes too hot. I mean, nowadays it's very difficult to live, for example, in areas with deserts. I mean, if you go to Death Valley in North America, the temperature rises to 50 degrees or above, and it's too hot for us to live in. It's too hot for any animal to live in. So if the temperature rises, it means that, well, people have to live on another place on the Earth, which could become overcrowded. So too many people. It means that we can grow less food. I mean, there's not food enough for us all. So that could cause mass extinction. Second one, meteorites. Of course, that's a problem. Why is that a problem? When a meteorite hits the Earth, it kills everything which is on the surface, of course, because a meteorite could be pretty big. They suppose that it happened during the end of the Jurassic, so that the latest dinosaurs actually died because of the fact that these meteorites fell down on the Earth. Another big problem, diseases. Well, we know all what happens to our planet when we got a disease. I mean, 3 years ago, we had a little disease which was floating around our planet, named COVID-19, and it had influence on the amount of people on our planet. I mean, we are lucky that we can, well, get people better because we do have medicines and all kind of stuff. But if they did not exist, I think a few million people on our planet would have died because of COVID-19. If you have a look at the past, and then we're going to the 16th century, there were several plagues which killed lots of people because there were no medicines in that time. So a big problem. And of course, diseases existed years before even people did live on our planet. So diseases could kill animals, of course, as well. Other problem, volcanism. If a volcano erupts, it creates ash. And ash into the atmosphere works like a mirror. It reflects the sunlight. It means that the sunlight won't get into the surface of the Earth, so the radiation can get to us or to animals. It means the temperature drops. It gets cooler on our planet. Well, if it gets cooler, certain animals can't live because they need sun to get warm. On the other hand, when a volcano erupts, it creates a big emission of CO2 and methane in the atmosphere, and those are greenhouse gases, which tend to create a hotter planet. Well, when the temperature rises, certain locations on our planet are not that nice to live on. So that could well, give a problem for the living creatures on that planet as well. So you see that during the time, several mass extinctions actually emerged out of climate change, meteorite, diseases, volcanism, all kind of things. So that could happen again. I mean, the disease that we already see 3 years ago, but volcanism is possible. I mean, if you're going to look at Northern America, when you're looking here in this region, we do have a national park, Yellowstone National Park, which contains a supervolcano. And if that volcano erupts, we do have a big problem. They think that if it erupts, well, a very big part of North America will be gone. So it has an enormous influence on the way our planet looks. So that could be a problem. Well, I want to show this a bit bigger. This is not in your book, but it shows the mass extinctions pretty well, because you can see the drop in the graph, and of course the rise of the graph as well. And we're here somewhere, and maybe there will be a drop again, and then that were us, and we are gone. So that was it. That was the thing to tell you today. I hope that you get an impression of the way our world has developed during the past billion years, and it's quite difficult to understand everything that happens. But I hope that it gives you, well, an image of how our planet looked like many years ago.